Polar coordinate system. A polar coordinate system is a plane with a point O, the pole, and a ray from O, the polar axis. Each point P in the plane is assigned polar coordinates as follows. R is the directed distance, or the magnitude, from O to P, and theta is a directed angle whose initial side is on the polar axis and whose terminal side is on the line OP. As in trig, we measure theta as positive when moving counterclockwise and negative when moving clockwise. If r is greater than 0, then P is on the terminal side of theta. If r is less than 0, then P is on the terminal side of theta plus pi. In other words, if we have this angle and r is positive, it goes along the angle. But if we have a certain angle but r is negative, it'll go along that angle but in the opposite direction. We can use radian or degree measure for the angle theta. Point A can be located by using the Cartesian coordinate system or polar coordinates. So we have this point A, and it is at 1, 2, 3, 4, 1, 2, 3, 4, 5. So it's at point 4, 5. And that's the Cartesian coordinates for point A. We could also find A by using polar coordinate system. We would need the length of the radius of a circle that passes through A, and we would need this angle. And we could do that by using the Pythagorean theorem to find r, the radius of the circle, and it would be 16, actually, this side would be 4, this side would be 5, so it's the square root of 16 plus 25, that's the square root of 41, and then we could find this angle by doing the inverse tangent of 5/4, whatever that would be. Example 1, plot the points with the given polar coordinates. So the polar coordinate would be a radius of 2 at an angle of pi over 3. So we would have to go to the second circle if each circle has a radius of 1 more than the previous. So there's the second circle, and pi over 3 is about right there. So there's the point 2 pi over 3 in polar coordinates. For letter B, or point Q, we'd have to go to the second circle. So here's a radius of 1. Here's a circle of radius 2, and we'd go to the angle 3 pi over 4, which is 3 pi over 4, but since this is negative, we're going to go in the opposite direction. So the point is right there. For letter C, or point R, we'd have to go to the third circle. There's 1. There's a radius of 2. Here's a radius of 3. And we have to go negative 45 degrees. So that would be down there, right there. There's point R. Each polar coordinate pair determines a unique point. However, the polar coordinates of a point P in the plane are not unique. In other words, if you have the point, let's say the third circle at pi over 6, that's a unique point. There's not another point that has this as coordinates. But we could get this point using different coordinates. So we could say negative 3, and we could go to 7 pi over 6. So that is a unique point, but these two are the same point. The coordinates r theta plus 2 pi n, in other words, all the way around the circle, and negative r theta plus pi all name the same point. In general, the point with polar coordinates r theta also has polar coordinates r theta plus 2 pi n, or negative r theta plus 2n plus 1 pi. Now what this does is it creates an odd number. So in other words, theta plus 3 pi. Where n is any integer, in particular the pole has polar coordinates 0 theta, where theta is any angle. So as long as the radius is 0, we're talking about right down the middle, the pole. Example 2, if the point P has polar coordinates 3 pi over 3, find 3 additional pairs of polar coordinates for P. So let's find the point 3 and pi over 3. That'd be 1, 2, 3. That'd be right there. Find 3 additional pairs of polar coordinates. Well, it's the exact same point we're looking at, but how about we go in the opposite direction? So what if we went negative, let's see, 1, 2, 3, 4, negative 5 pi over 3. And we'd be still on the third circle. Let's get this point in another way. What if we went to 2 pi, negative 2 pi over 3. So negative 2 pi over 3, and then go negative 3. So we would go to this point right here, but then go backwards 3. Let's get this point one more time. We could go to 1, 2, 3, 4 pi over 3. So we'd go 4 pi over 3 and then go negative 3. So that'd put us right here and then go backwards to the point. Coordinate conversion. When we use both polar coordinates and Cartesian coordinates, the pole is the origin and the polar axis is the positive x-axis. By applying trigonometry, we can find equations that relate the polar coordinates r, theta, and the rectangular coordinates x, y of a point P. Let the point P have polar coordinates r, theta, and rectangular coordinates x, y. Then, x is equal to r cosine theta, y is equal to r sine theta. Now on the unit circle rather, let's look at the unit circle. When the radius is 1, this point right here is the cosine of theta, and this is the sine of theta. So this is your x and this is your y. Well, if the radius happened to be 4, then this point would be 4 cosine theta, and this would be 4 sine theta. So x is equal to the radius times cosine of theta, and y is equal to the radius times the sine of theta. R squared equals x squared plus y squared. That's just using the Pythagorean theorem. And the tangent of theta equals y over x. In other words, opposite over adjacent. These relationships allow us to convert from one coordinate system to the other. Example 3. Find the rectangular coordinates of the points with the given polar coordinates. So we have this polar coordinate. Here's the first circle. That has a radius of 2. This has a radius of 3. And we want 5 pi over 6. So that puts us right there. And we want to know the rectangular coordinates. Well, x is equal to, we have a radius of 3, cosine of 5 pi over 6, and y is equal to 3 sine of 5 pi over 6. So we have the point, let's see, the cosine of 5 pi over 6 is negative square root of 3 over 2. So we have negative 3 square root of 3 over 2, and the sine of 5 pi over 6 is 1/2. So the y-coordinate is 3/2. With letter B, we have negative 225 degrees. So here is negative 180, and another 45 is negative 225, and of course, we're on the second circle. So x is equal to 2 times, actually negative square root of 2 over 2, and y is 2 times positive square root of 2 over 2. So we have the coordinates negative square root of 2 comma square root of 2. When converting rectangular coordinates to polar coordinates, we must remember that there are infinitely many possible polar coordinate pairs. In exercise 4, we report 2 of the possibilities. Exercise 4, find 2 polar coordinate pairs for the points with given rectangular coordinates. So the x is equal to negative 1 and the y is equal to 1. So we know that r squared is equal to x squared plus y squared. So r squared is equal to 1 plus 1. R is equal to the square root of 2. So we have square root of 2, comma, and now we need the angle. Well, the tangent of theta is equal to y over x. So the tangent of theta is equal to 1 over negative 1. So theta is equal to the inverse tangent of negative 1, and that is negative pi over 4, or negative 45 degrees. We have the point on letter B, 3, 0. 1, 2, 3, 0. That's the point right there. So the radius is equal to just 3, and the theta, or the angle, is 0. So even in polar, this is 3, 0. But this is an x and a y, and this is over here an r and a theta. Convert the polar equation to rectangular form and identify the graph. In this case, we have r is equal to negative 2 over The reciprocal of cosecant is sine. So we have sine of theta, and r sine of theta is equal to -2 when we multiply both sides by sine theta. Now what we're trying to accomplish is to get this r sine. R sine is the same as y. So we'll go back. We have r sine, and we have y is equal to -2. That's the Cartesian equation for this. It says identify the graph. This is a line. On letter B, we are going to multiply both sides times r. On the left side, we have r squared, and on the right side, we have -4r cosine of theta. And on the left-hand side, r squared is equal to x squared plus y squared. Here we have x squared plus y squared is equal to -4. R cosine is x. We have -4x. Now we can add 4x to both sides. We have x squared plus 4x plus y squared is equal to 0. Now let's set this up to complete the square on x plus something plus y squared equals 0 plus something. To complete the square, we take b divided by 2, that's 2. Square that, that's 4. So we're going to add 4 to both sides. We have x plus 2 squared plus y squared is equal to 4. And this equation is a circle. Exercise 6. Convert the rectangular equation to polar form. X is equal to r cosine of theta. So we can make that replacement. And usually with these, we have r equals. So we have r equals 5 over cosine of theta. R is equal to 5 times secant of theta. On letter B, we have 3r cosine of theta plus 4r sine of theta equals 8. And we can factor out an r. We have 3 cosine of theta plus 4 sine of theta is equal to 8. And now we just do a little division, and that's all we're going to be able to do to this one. So we have 3 cosine of theta plus 4 sine of theta. With letter C, this is a circle with center 1, -4, and a radius of the square root of 17. Let's multiply all this out. We have x squared minus 2x plus 1 plus y squared plus 8y plus 16 is equal to 17. We can minus 17 from both sides, and we get x squared plus, let's put this y squared with x squared, minus 2x plus 8y is now equal to 0. Well, x squared plus y squared is equal to r squared. We have minus 2r cosine of theta plus 8r sine of theta is equal to 0. Let's factor an r out. We get r minus 2 cosine of theta plus 8 sine of theta, and this is supposed to be equal to 0. So now either r equals 0 or r minus 2 cosine of theta plus 8 sine of theta is equal to 0. Now if we look at r equals 0, that's the pole, and so that's just 1 point. And this is certainly not 1 point. This is actually a circle with a radius and an offset center. So it must be this one right here, and usually we have equations that say r equals. So we have r equals 2 cosine of theta minus 8 sine of theta.